So we're talking about superconductivity in this class. Now it was observed that at a very low temperature of 4.2 Kelvin, mercury wire suddenly lost its resistance. So it was seen that a mercury wire had a lot of resistance like this. Definitely it went to zero at about 4.2 Kelvin. So this process of having zero resistance at a certain temperature is called superconductivity, and usually metals at very low temperature, like in this case mercury, they exhibit this superconductivity. Apart from this diminishing of resistance, there are other phenomena occurring in superconductors. One of them is exclusion of magnetic field. So if you have a superconductor like this, again at very low temperature, and if you allow magnetic field, it will not allow magnetic field to pass through it. To simply make the magnetic field exclude itself. It will not be able to coincide the superconductor. This is called Meissner effect, exclusion of magnetic field. However, here we have to see that this is valid for a certain critical magnetic field. Like in this case, this is valid when the temperature is less than a certain critical temperature, which in this case is 4.2 Kelvin. Similarly, in Meissner effect also, the magnetic field should be less than a certain critical magnetic field. If it exceeds that, then it can penetrate actually. And this exclusion of magnetic field makes this superconductor as a perfect diamagnet. Those diamonds are supposed to exclude the magnetic field also. Now, what is the reason of this superconductivity? The reason was given by Bardeen, Cooper, and Schaeffer. So it is known as BCS theory. What they suggested is that as the temperature is very low, so there are very less molecular motions or lattice vibrations taking inside the material. So that is why in an ionic so these are considered as the lattice points, positive lattice points, and here between them there is a flow of electrons. This is the normal scenario inside a metal. Now, as the temperature is low, extremely low, so these ions or these positive points, they are not vibrating or vibrating at a very low frequency. That is why what happens is that while an electron is passing through one of the positive ion pair, it attracts the electron towards itself. So the scenario now becomes something like this. So there is attraction of the positive ions towards itself. Now, due to this attraction caused by the electron, repulsed by the electron. As the positive ion comes closer to it, so a positive charge surrounding this whole area, it actually develops. Delta positive and delta positive. But that is why the incoming electron from the other side, it actually gets drawn towards this. So what happens is that we have an electron pair. Electron pair is formed, and this is called a Cooper pair. Okay. And minded that this is a boson, because half integral spins of both electrons may get integral spin, and it follows Bose-Einstein statistics. So this is the mechanism of superconductors, the BCS theory. Now, apart from the metals at low temperature, there has been certain ceramic compounds as well which show superconductivity, and these are called high temperature superconductors. And why they are called high temperature? Because compared to the temperature of metals, critical temperature of metals, critical temperature of these ceramic substances are pretty high. For example, very common material to be showing superconductivity is YBA2Cu3O7, having a critical temperature of 90 Kelvin, and we also have material having critical temperature of 133 Kelvin, that is HgA2Ca2O8 plus X. So these temperatures are having a pretty high critical temperature. Now, the colder is a superconductor, the more current it can carry. So temperature is directly proportional to the current, or inversely proportional to the current. So let me put it: the colder is the superconductor, the higher is the current flowing through it. Now, if you plot, as we have plotted resistance versus temperature, if we plot magnetic field, applied magnetic field versus temperature, so again you can see that for the superconductor, it will fall down to a certain temperature. That means this is your TC and this is your HC, the critical magnetic field, critical temperature. This is for the superconductor. However, there are two types of superconductors. One is called type 1, having a single critical temperature, and another one is called type 2, having two critical temperatures. So for a type 2, you have a critical temperature number 1, which is called HC1, and you have a critical magnetic field HC2, and so in between these two, this is called the mixed or vortex or mixed state. Now, as the resistance inside a superconductor is 0, so can it be called a perfect conductor? This is a question. So let us try to see whether it can be called a perfect superconductor or not. Now, as we have seen that in a bulk superconductor, inside the superconductor, there is magnetic field. So let's put B is equal to 0. Now, now B is equal to also the applied magnetic field plus the magnetization that is taking place. It's magnetic permeability into magnetization. Now since B is equal to 0, so the applied magnetic field is again equal to minus mu 0 m. It's quite understandable. Now in a superconductor also the resistivity rho is equal to 0. Now from Ohm's law, E is equal to rho into J, where J is the current density and R rho is the resistivity. So making rho is equal to 0 implies that E is also equal to 0. Considering these two cases, if we again go to Maxwell's equation, according to Maxwell, a change in electric field should cause change in temporal or change in magnetic field, and which is supposed to be 0 if E is equal to 0. So that again implies that the magnetic field is constant, and it implies that the flux through the metal cannot change on cooling the transition. So if we flux can't change, so this is actually contradicts the Meissner effect, which says that flux is excluding the magnetic field, so it has to be some change. So therefore there is a difference between a perfect conductor and a superconductor. So perfect conductor is not exactly a superconductor. Perfect conductor is not a superconductor, because perfect conductors, when placed in magnetic field, cannot produce a eddy current. Screening of the magnetic field cannot take place. Now another aspect of the superconductivity is called Josephson junctions. According to Josephson junction, the basic idea is if you have two superconductors, SC1 and SC2, and you connect these by an insulating layer. This is an insulator. So according to Josephson junction, this is actually Josephson junction. So actually what it says that a Cooper pair, so let's call it as an EE, a Cooper pair can actually tunnel through one superconductor to another superconductor. That means the wave function of the Cooper pairs on each side of the junction to penetrate. So wave functions of Cooper pairs, they actually penetrate through the insulating layers. And the insulating layer is of about 2 nanometer on average. Now we have an AC Josephson effect, which says that the current density Ij is equal to I max into sine phi. Phi is the phase difference between these two functions. This is the DC Josephson effect, whereas the AC Josephson effect tells that there is a change in the phase that is taking place between the phase difference actually changes with time, and it is equal to 2 into VE by H. So that means the current density is varying sinusoidally with time. A major application of these Josephson junction or Josephson effect is in a device called SQUID, superconducting quantum interference device, and it is a very highly precise instrument to detect the magnetic field of a material.